Good afternoon. My name is Zishan Li from ECE department. So I will be, it's a great pleasure for me to introduce today's speaker, Professor Vijay Kumar from University of Pennsylvania. And actually, for many of us, this name is well known, from the TED Talks, that is known globally. So there's really no need to introduce him. But actually, Vijay and me, we have lots of cross points. We were graduate students at the same time, and also we studied our professional career as a young assistant professor 25 years ago. I'm at New York, and he is Philadelphia, just a couple of hours, a few hours drive away. We are still young, right? And we work in very much a similar area, which is grasping manipulation. And during lunch, we talked so much has been changed over the last 25 years, in the field we were in, and also the broad area of robotics. From a small area now, lots of tremendous opportunities. And the VGA was director of the well-known GRASP lab, at UPenn, and he served on various positions in the department, in the university. And his most recent assignment was assistant director of White House Office of Science and Technology Policy. So deciding on the major robotics policy in the United States. And a few of us also read the robotics roadmap, a very thick document describing the roadmaps and the policy of robotics industry research in the United States. And Vijay is one of the organizers of that event. And of course, he received lots of honors and lots of awards, so I'm not going to list it. And he is most recent member of the US National Academy of Engineering. In fact, in this area, I think this is the second time I come to this lecture hall. The last talk was by Professor Richard Murray from Caltech, and those are the same classmates of the National Academy of Engineering. So without further ado, so Vijay, I will give the mic to you. So welcome.
Thank you very much for that very kind introduction, Zishan. And thank you for inviting me to spend a couple of days here in Hong Kong. It's nice to escape from the cold in Philadelphia. My wife always complains when I leave is when the snowstorms start, and it's very convenient. Anyway, it's a great opportunity for me to share with you some of the work that my students and I have been doing on aerial robots. What I'd like to do first is, however, set the context for what I mean by aerial robots. And by the way, this is going to be a fairly high-level talk, so if there are any questions you have about details, I'd be happy to answer them. So do interrupt me. So just setting the context, the first thing I want to point out is there are lots of things that fly in the sky and that are apparently autonomous, but are not. And these are things we are not really interested in. These are things all the way over on the right-hand side of the scale, vehicles that weigh thousands and hundreds of thousands of pounds. And they're essentially, for practical purposes, they're remotely controlled by operators on the ground. In fact, a lot of these require a 10-to-1 to a 20-to-1 crew-to-aircraft ratio. On the other hand, the kinds of things that we're more interested in are on the left side of the scale. And these are helicopters that fly indoors. And as I'll explain shortly, all the helicopters we design have either 4 or 6 rotors, sort of so-called quadrotors or hex rotors. And the smallest one is about the size of my palm. And we designed them with the goal of hovering and flying in environments like this, indoor environments, flying through doorways, through windows, and so on and so forth. And this is particularly important if you think about applications such as search and rescue. So here you see a couple of pictures from experiments we did not too long ago in Sendai after the earthquake. We went into collapsed buildings to see if we could actually map the buildings to verify the structural integrity. And so these vehicles needed to be able to fly through doorways, in fact, buckled doorways, as you see here. We also want to use them for applications in security and first response. So here you see a very simple application of one of our robots that's flying about 80 feet off the ground and able to track objects on the ground. And something like this you can program to be autonomous and perform surveillance and look out for suspicious objects, track cars, for example, or moving cars, and so on and so forth. Ideally, we'd also like to be able to do things like this. So what you see here, so this is not sped up. This is just a robot flying through buildings. There's some manual interactions here, and some of this is autonomous. But what we'd like to do is have them go through buildings. We tell them, go in and find out what's there and tell us if there's something that is unexpected, so that if you have a situation where human first responders need to go in, you want robots to be there and provide an integrated view of what's inside the building before the human responders actually go in. So I'll be telling you a little bit about how we enable autonomous flight for operations like this, for example, flying through hallways. And then lastly, we're interested in applications in farming. And so these are experiments we conducted not too long ago at the Penn State campus, which is distinct from University of Pennsylvania in Biglerville, Pennsylvania. So these are apple orchards. And what we'd really like to do is to be able to fly through the tree lines, fly above the tree lines, and be able to map out individual trees, estimate the canopy size, project the growth rate, count the number of apples on trees, and be able to distinguish. No, this is a serious problem, by the way. So, you think about a manufacturing plant. You go and ask the plant foreman, how many widgets do you have of type X or type Y? And there's an answer to it. You ask a farmer, how many fruits do you have? The person, there's no estimates. So we'd like to be able to do this and plant by plant be able to document what's growing, how fast it's growing, and also monitor the state of plants. I mean, using some very simple techniques, we think we can actually detect, for example, which plants are actually suffering from heat stress, which plants are suffering from water stress. And here are examples of three-dimensional maps that we can create on the fly. And in this particular case, we have three robots that are simultaneously accomplishing this operation. And there are many other exciting applications. So one of our spin-off companies, KML Robotics, has actually partnered with a company in China to create these flying eyes for aerial photography. A more interesting application, however, is a robot for inspecting the inside of hydroelectric power dams. So this is actually the interior of a penstock, which feeds the water from in a dam through a turbines downstream. And just going inside and inspecting the interior to detect rust spots like this. So we'd like to be able to do this autonomously. Another company which is actually looking at developing a swarm of quadrotors with small ground-penetrating radars. The idea is that if you have military convoys, typically they only can go at 2 to 3 miles an hour because somebody has to go in front and sweep the area to see if there's any explosives. Well, if you have something like a ground-penetrating radar in this swarm that's sort of patrolling it, you can potentially increase the speed by an order of magnitude. So we'd like to be able to do things like this. And then finally, a company in California that's interested in monitoring construction sites. So this is a football stadium. For those of you who know about American football, this is a new 49er stadium in Santa Clara. So we'd like to be able to solve problems like this, which involve monitoring and logistics. And again, the vehicle of choice for us is a quadrotor. If you actually want to build large teams of robots, you want to pick a design that's mechanically simple. And although there are lots of ways you can build microaerial vehicles, so today, the easiest thing to build is a quadrotor. You have a rigid frame, motor, props, as the robot turns, you generate these large gyroscopic moments. Those are all transmitted through the motor shaft to this rigid frame. There's no flapping of the blades or anything like that. It's just a very robust design. So here you see a picture of one of our robots operating indoors with motion capture systems, and I'll tell you a little bit more about that as we go along. So the nice thing about this design is you can really scale it up for mass production if you wanted to, or just rapid prototype it in your lab. And there's this pyramid chart that sort of describes how robotics is involved, but in particular how UAVs have evolved. So at the top of this chart is, of course, all the expensive vehicles that you can buy, costing lots of money, which is beyond sort of university budgets, if you will. But also from a standpoint of academic interest, there's very little research you can really do on things like global hawks and predators. On the other hand, you can ask how you can go down the pyramid. At the bottom of the pyramid is actually all the stuff that you see enabled by consumer electronics. Think about smartphones, cameras, and so on, or computers. And there's a lot of hardware now that's really become inexpensive. So the price to performance ratio of different types of sensors, different types of processors has really come down. And as a result, there's a huge industry about building toys, building hobby kits, and so on. So the question we ask is, what component technologies can we really take from this and leverage that to build autonomy into the systems and agility into these systems? So I don't know what this market is, but if you look at this price, maybe somewhere in the order of $1,000 to $10,000, you could really think about small units and maybe lots and lots of these to drive down the price eventually. But really building on hardware that's off the shelf and then software that's customized to the specific application. So that's sort of our goal. And again, as in many things, size does matter, and you can actually look at scaling effects. You can look at basic laws of physics. You can look at inertia. You can look at aerodynamic forces. And if you take the characteristic length R and you squeeze it, you'll find that things like mass and inertia go down dramatically. Actually, so does thrust. But if you look at the scaling of the aerodynamic forces and the rigid body dynamics, you'll find that actually the maximum acceleration you can develop goes inversely as R. So if you take your typical platform, you scale it down by a factor of 2, the acceleration actually doubles. And more importantly, the angular acceleration actually goes up by a factor of 4. So we like to use this and create really small robots that can maneuver very quickly. So our smallest robot is actually the one shown over here, which can perform these flips in about half a second, which means it really needs to accelerate from 0 degrees per second to a top speed of about 2,000 degrees per second in roughly a quarter second. And so we work very hard on building controllers that can stabilize these rotations, and I'll say a little bit about this going forward. And by the way, this is the work of Daniel Mellinger and Alex Kushlia, who are principals of K-Mel Robotics, the spin-off company that I told you about earlier. So what I'd like to do in the next 40 minutes or so is tell you about some of the research problems we're trying to tackle. First, problems in dynamics, control, and planning of quadrotors, in particular focusing on agility and autonomy. Second, a fundamental problem that has to do with state estimation. So if robots are to be autonomous, they have to figure out where they are in this world without relying on external sensors like the motion capture cameras I showed you earlier, or GPS. You cannot take GPS for granted, particularly indoors. And then lastly, talk a little bit about how we think about swarms of these cooperating to do different tasks. So those are sort of the three areas that I thought I'd hit on. And again, if there are questions, I'll stop briefly at the end of each area and take your questions before moving on. Okay, so let's first start by talking about the dynamics. So again, a quadrotor consists of, and I'm going to assume that most of you are not familiar with this, so this is a very sort of a basic introduction to how things work. So a quadrotor, as I told you before, is an aerial robot, has 4 rotors. And the most important thing you need to know is how to control the roll and pitch. So at equilibrium, all the rotors are spinning at equal speeds, and the thrust from the rotors compensates the weight. Of course, if you wanted to roll or pitch, you take one rotor, spin it faster, and that generates more thrust than the other one, and that results in a pitching motion. Or you can also think about it rolling out of the plane. And if you want to go it in the other direction, you just reverse the order of the differences in the rotations. And we work quite hard on designing controllers that can stabilize roll and pitch through 360 degrees. And what you see here is some sense of how robust the controller here is. You see Daniel Mellinger just throwing the robot into the air, and we need to have it stabilize automatically. And one of the things you can actually show is that this is a controller that works on the group of rotations, and it's stable almost everywhere. The basin of attraction is almost everywhere. In fact, if you look at this inequality, this basically tells you that the rotation matrix can be far away from the desired rotation matrix. This is an equality when the rotation is exactly opposite. So in other words, I want to get to this configuration, but I'm starting off in that configuration. So that's the only point where it fails. This equation basically tells you that if you look at the allowable errors in angular velocity, that's bounded by this right-hand side. And a key thing I want to point out is if you look at the denominator here, this is the smallest eigenvalue of the inertia tensor. So what this is telling you is if I can make the robot really small, this inertia tensor is small, and therefore the denominator is small, and the right-hand side grows bigger. And that tells you that the allowable errors in angular velocity can be larger. So again, this idea that as you make things smaller, your controllers actually become better and better, and you can leverage that as you see in this particular picture. Translation, however, is a little more complicated. So if I want to take this robot and have it translate from one position to another position, this is hard to do because, remember, the thrust is actually in the vertical direction. So the only way you can get it to go horizontally is by pitching it forward, redirecting the thrust. And then when you're going at maximum speed, you have to start slowing down as you get to the final position, which means you have to pitch backwards and reverse the thrust. So mechanical simplicity means that you have to spend quite a bit of effort in the control. And then when you get to the end position, you have to pitch it back to the position you want to be in. So all of this needs to happen seamlessly without the user sort of worrying about the controls. And remember that when you put all of these things together, you can't ignore or you can't decouple the position orientations. They're all coupled. And plus, you also have to consider the velocities. In fact, if you look at the state space, and if you look at the global nature of the state space, it's best described as a tangent bundle in a Lie group type setting, and the Lie group in question is the Euclidean group. So you really have to figure out the dynamics on this group and design controllers and trajectories on that group. So fortunately, there's a differential structure that actually simplifies the treatment of the mathematics of this problem. So it turns out that there's a map between this space and a space that's almost flat, such that all realistic trajectories, all trajectories that satisfy the laws of physics, actually map to sufficiently smooth trajectories in this almost flat space. So this almost flat space consists of x, y, and z, which is actually flat. This is the Euclidean space we live in. But there's another angle here, which is the yaw angle. So this yaw angle is not truly flat, because if yaw angle has the topology of a circle, so if I were to chop the circle and stretch it out, then it becomes flat. So if you allow me to do that, then the point I'm trying to make here is that any realistic trajectory I can generate here corresponds to a trajectory that lives in this flat space and is sufficiently smooth. In fact, the property I want to insist on is that it's 4 times differentiable. So this property is called differential flatness. And if you can show that the system is differentially flat, then essentially the problem of planning trajectories from A to B gets simplified by just transforming it into this flat space and then finding sufficiently smooth trajectories in this flat space. In fact, in this flat space, if you have obstacles, all you have to do is find trajectories around those obstacles and then map it back into that flat space. And we find trajectories that minimize this functional, which end up minimizing the 4th derivative position and the 2nd derivative yaw. So if you take this functional, you generate smooth trajectories in this flat space, and you have to make sure that you satisfy these inequalities that the obstacles impose on you. So that's the general setup, and I can just show you a few videos that illustrate how the robot flies using this sort of trajectory planner. So here's the robot going from point A to point B through an intermediate point C, and you'll see that although the trajectory that it plans is flat, when you convert it into this into SE3 and the tangent bundle, you'll see that you generate these large roll and pitch angles that you would not have gotten in the flat space. But the planner is actually agnostic to all of that. All the planner is saying is I want you to go from A to B through this point C from a position of zero velocity and ending up at a position B with zero velocity. And everything else happens seamlessly under the hood. And this optimization problem that we have, we can solve several tens of times a second if necessary to generate trajectories and keep updating them depending on how the environment changes. So this simple strategy we can also use to go around obstacles or through obstacles in this case. So you see this robot flying through hoops. Again, you have to remember that everything in the environment is known precisely. We have these motion capture cameras that's telling the robot where it is and where obstacles are 100 times a second. So in fact, one of these hoops is thrown into the air, the robot knows where the hoop is, how it's falling. Well, it can extrapolate from the laws of physics, it can predict how the hoop is falling and then plan trajectories through that. And we have the orientation controller that essentially tracks the required orientation that you plan. And then there's an outer loop, a position controller, which I haven't talked about, which essentially does the rest. So all of this stuff happens on board the robot. The planner actually resides off board, and then there's communication, wireless communication from the planner, which is on a bigger computer, to the onboard controller, which sits on top of the robot. Not only this, but you can do more fancy things. So we'd love to be able to do what this bird is doing. This is a bald eagle fishing. And we'd love to have our robots be as aggressive, as agile, as dexterous. And here's our robot that looks like a burrito, but it's actually just a rolled up tube. But you can see that we can actually duplicate this. Actually, it turns out that this particular dynamical system also has this property of differential flatness. And the same theory that we have before essentially allows us to do the exact same thing that you see in this particular video. And this is work of Justin Thomas, which in 3 months he'll be presenting it here in Hong Kong at the ICRA conference. However, everything that I've told you about really relies on these motion capture cameras. So you can see these motion capture cameras on the top, and you'll also see that the robot is equipped with these reflective markers. And this is what allows the system to know exactly where the robot is at 100 times a second, and again, with errors that are of the order of millimeters. And the reality is, we don't have those we don't have that system. Unlike bigger aircrafts, we don't even have access to GPS. And in fact, even if you did have GPS, in shadows of buildings like this, you're not going to get GPS. And certainly when you're indoors, and again, the kinds of missions we want to do, operate indoors, there's no GPS, and you want to maneuver, this becomes a problem, especially at high speeds. So what I want to talk about next is how we address this problem of estimating the state in such indoor environments and how that will lead us to autonomy. But let me just pause here and see if you have any questions on the first part before I move forward. Yeah. So you need 4 in order to, so you can show that less than 4 results in undesirable properties. If you want to stabilize all the motions, you need 4. You can certainly do 5, 6, and so on. In fact, if you add more, you get more robustness. You also can make the blade sizes smaller, which is attractive if you want to. I have a lot of students who go around with, you can see I actually have my little finger taped up, so those blades can be pretty vicious. And so if you make the blade smaller, that's better. So there are some benefits to that, but the benefits, if you compare them to the disadvantage, which is you add more motor drivers, more motors, and it's just not worth the trouble. Any other questions? Yeah.
You design the trajectory from A to B, you might have a lot of multiple choice. always looking to optimize.
So we're looking for this problem turns out to be convex. So if you say that I'm going to take this quadratic functional, which depends on the higher order derivatives of position and the yaw angle, that turns out to be convex, and you can solve for it, and you'll get a unique solution.
But if you have a non-convex,
so I'll talk a little bit about that. So if you have obstacles and you want to stay outside the obstacles, that is inherently a non-convex problem. But we have ways of convexifying all of that, and the main thing is we cannot afford to have algorithms that hang in the middle of, when you do the optimization. So we try to get predictable performance, and that's one of the key things.
Are you really looking for a feasible solution? Are you really looking for optimal?
If you want to go quickly, you want the optimal trajectory.
Are you looking for us?
Right. And so this trajectory has time scaling properties that allow you to scale down and meet whatever other constraints you have.
Thank you.
Yeah.
So you may be going here later, obviously, Stefan. Do you ever use thrusters instead of, in other words, can you just use Quadrotor as a stable platform?
Oh, there are a lot of variants in this design. Like I said, I'm a mechanical engineer, so this is the simplest design you can kind of come up with. And it's the one that has served us the best. So we've built all kinds of devices, and this has sort of stood the test of time, if you will. Yeah.
Works nice.
Yes? Well, so I mentioned the effect of scale on the properties of the algorithm. So clearly, when you try to design the controller, you want to take advantage of scale. So the smaller it is, the more aggressive you can make it. To that extent, yes. So there's a model-based part, which obviously depends on the model, and then there's a part that's invariant to the specifics of the model. And I should also say there's a third part which essentially adapts to things that it doesn't know about. Like, for example, going through the hoops I showed you, we can actually make the hoops tighter. We can have the slots be we can have vertical slots that are just about the same width as the height of the robot, and having the robot go sideways. But if you do things like that, you have to really adapt to the aerodynamics. So then you really need to have some iterative learning scheme that essentially finds out what the right parameters are. So that part I didn't talk about. But there are these three parts to it, and all of those parts depend in one way on the specific type of robot you're using. But the design methodology is the same. Okay? So let me move ahead. Talking about unstructured environments, again, remember, no GPS, no motion cameras. This was our first attempt to build a robot like this. So this is about 3 years ago. Again, off-the-shelf sensors. The main sensor here is this laser scanner, which is made by a Japanese company, Hokuyu, which has a 270-degree field of view and can see about 20 to 30 meters out. And then this you can get with any Xbox. It's a Microsoft Kinect, which is essentially an RGB depth camera, which has a cone angle of about 40 degrees and can see maybe 3 to 5 meters out. So this gives you a three-dimensional picture of what's in the environment. And that is one way you can actually map features in the environment to figure out where you are. So to those of you who might not be familiar with this idea, so I have a little cartoon that illustrates the problem we're trying to solve. So imagine you have a robot, and imagine there's an environment with 3 pillars. The robot doesn't know that there are 3 pillars in the environment, and it doesn't know, even if it knew there were 3 pillars, it wouldn't know where they are. And it doesn't know where it is in the environment. But imagine it's got this laser scanner that allows it to essentially determine the distance between the robot to the pillar. And that allows it to measure these distances, D1, D2, and D3. Now imagine it takes a step, and it has onboard inertial measurement unit that allows it to integrate the acceleration twice to get an estimate of how far it's moved to the new position. Now the new position, it gets, again, using the laser range finder, 3 different estimates of range, D1 prime, D2 prime, D3 prime. So the question is, can you, with the knowledge of these parameters, so there are 6 of these measurements and then 2 estimates of delta x, can you figure out what the real translation is and where these pillars are relative to the robot? And if you write down a few equations, you could quickly convince yourself that this is actually doable. You essentially have 8 unknowns. 6 unknowns have to do with the pillar locations, and 2 unknowns have to do with the robot displacement. And then you can determine what these quantities are by solving these equations. You have enough equations. And this problem is essentially called simultaneous localization mapping. You've not only figured out where the robot is, but also figured out where the pillars are. And in the robotics community, we call it SLAM. So this is sort of a key component technology, and we have to actually do this in real time. In the absence of motion capture cameras, you want to use SLAM algorithms to determine how far the robot is moved, and you want to do it 100 times a second to run the same control loops. And it has to be done on board. So if you want a truly autonomous robot, you can't really outsource some of the computing to an off-board computer. So our first attempt to do this relied, again, mostly on the IMU and the laser scanner, and to a lesser extent on the camera. And the key part of this is really looking at the laser and the IMU and getting some estimate of how far you've moved, this pose estimator that I told you about. The only difference now is that not only do I have to figure out how much I've translated in X and Y, I also have to figure out how much I've moved vertically and how much I've rotated. So all of that stuff is happening here. In fact, this takes up about 20% of our CPU, which is a 1.6 gigahertz Atom processor, a netbook-style processor. This is quite key. Once you can do that, you can start building a map, and this is sort of called an incremental SLAM map, which essentially builds an occupancy grid representation. So imagine every feature that I build, as I see in the environment, I put a box around it, and I create this world of boxes. That's happening over here, and that allows the robot to localize itself as it moves forward off those boxes. All of this flows into an extended common filter, which is essentially running at 100 hertz. Now, you would get 100 hertz input from the IMU, but what you really want to do is correct with 6 degree of freedom odometry, which is essentially the relative change in positions and orientations in 6 dimensions. You want to use that to bootstrap your EKF. So this is quite key. And then ultimately, we have a controller, the same controller that runs at 100 hertz. And an important aspect of this controller is you're also estimating these parameters. And this has to do with the unmodeled aerodynamics. So one thing you don't realize is if a robot is actually traveling, let's say, with a column of air below, and then it moves over onto another surface where the column of air is smaller, the lift that you get actually increases. This is called a ground effect, which is well known in aerodynamics. And you want to estimate that as you fly. We also have something called the ceiling effect, which most people in aerodynamics don't think about because helicopters don't fly close to ceilings, but we do. And the ceiling effect is actually the opposite. In the ground effect, you get push off from the ground, and the ceiling effect, you actually get sucked into the ceiling, which we found out the hard way. But the robot needs to adapt to that. So all of this stuff is happening on board 100 times a second, and that's key to making this thing work efficiently. So this is a work of Xiaoji Shen, who's actually here today, as it turns out, and Nathan Michael. And you can see the system, the early system that we built. The robot takes off outside this building. It's never been inside this building. This is what it sees. The laser scans that it gets are being translated to the map. And Xiaoji is sitting outside on his laptop, and he sees this map, and he's able to command the robot by clicking on points on the screen. So he clicks on this point. The robot plans a trajectory. You'll see he clicks again, and there's a red snaking trajectory over there that the robot plans. And as it moves, it gets more and more information, getting a better map, and that goes back to the human operator, allowing the human operator to command the robot better to get more information. So this process involves the human interacting with the robot to explore this environment in which he or she has never been before. So this is a pretty important tool. Again, you think about first response, security applications. This is something that you can really use to explore buildings that you don't want to enter in case there's any source of danger for humans. You can also get the robot to automatically figure out where to go. And this is this idea of autonomous exploration where we have this information theoretic view of maps. And the question is, what steps can the robot take to maximize the amount of information gathered? And so in this video, you'll basically see this is sped up 8 times. You'll see the robot in a fairly complex building. and you'll see it creating this map and figuring out what positions to go to in order to collect more information. And this map is being built on the fly, and here there's zero human interaction between the operator and the robot is building this map on its own. So tools like this, again, can be very useful. As you can imagine, if you have, for example, a terrorist anti-terrorism operation, or you have an active shooter spotted in a building, and you want to go in and see what's in the building, something like this can really be used to good effect. So the problem with this design, of course, is that it's quite big. So this weighs about nearly 2 kilos. So I started by telling you about these palm-sized robots, and all of a sudden I have something that's quite big. It can still go through doorways. It weighs about 2 kilos. More importantly, it consumes about 480 to 500 watts of power. So that's a lot of power. It's half a kilowatt of power for something that's essentially moving around. It's pretty small. It's not doing a lot of physical work in the sense of picking up objects or anything like that. All it's doing is wandering around and mapping and navigating buildings. And why is that? Well, we wanted to put all the sensing on board. So we started off by saying, hey, let's put a laser rangefinder on board. Well, that added some mass to it, and because of that, we had to make the motors bigger. Once you make the motors bigger, you have to put bigger batteries on it. And once you make the batteries bigger, you have to have bigger props, and then that takes you in the wrong direction. It scales up as opposed to scaling down. And it actually gets worse, right? So if you look at all the lithium polymer batteries, which is what we use, which are available today, so we actually conducted tests in terms of specific energy, how much energy is stored per unit mass, how much power you can get out of these per unit mass. And this is a plot of that. And you'll notice that there's nothing on the right-hand side of this plot. And so if you want long missions, right now, at least with the state-of-the-art in lithium polymer technology, you're not going to get that. And just by way of comparison, if you look at humans, so this is a schematic of adipose tissue, fat. So we're way off scale. We can carry several orders of magnitude more energy than lithium polymer batteries can. So that's one part of the story. The other part of the story is that if you look at the quadrotors we're building, they're actually very power hungry. They consume about 200 watts per kilo. So anytime you choose to put a sensor on board, you really have to think about not the power that it consumes, but the power that's required to hover with that sensor on board. So if you put a laser on board, you're essentially going to drive up the amount of power that you need to power the laser because you have to carry it. So this is a very bad figure to deal with. And again, to compare with humans, if you look at the human being that possibly burns the most amount of power, this is Usain Bolt. In a 100-meter dash, he consumes about 20 watts per kilo. So we're an order of magnitude worse than that. So not only can we carry a lot of energy, we're also horribly inefficient in terms of navigating. Of course, it's unfair to compare something that's flying with someone who's running, but it's a good comparison point. In fact, there's another comparison point. This is Lance Armstrong bicycling for 20 minutes, and this is true whether he has steroids or not. He's burning the same amount of energy. So roughly 6 watts per kilo, and again, orders of magnitude smaller. So what's our solution? Well, we're going to be stuck with this chemistry at least for the next several years, but what we can try and do is work on this part, right? So we can try to lose weight, right? Everything is normalized to mass. So our first attempt to do that was to come up with something without any lasers. So this is what I call a flying smartphone configuration. So if you look at your smartphone, it has 2 cameras and it has an IMU. And that should be enough to make your smartphone fly. Well, you have to add 4 rotors and 4 props to it, but that's the basic configuration. And actually, my iPhone has roughly the same computational capability that this robot has. So this is, again, work of Xiaoji and Yash Mulgaonkar, another student. So the design we came up with, and this is a couple of years old, this is about 740 grams. We're down by a factor of 5 in terms of power consumption. And the key idea here is that you do all your triangulation. you're mapping out with just the 2 cameras on board. So how do we do that? Well, this is a clever combination of using the structure that's there in the environment and thinking about the problem, the SLAM problem, in its entire glory, and then slicing it so that you can solve sub-problems in real time. So if you think about it, when you're navigating through these environments, these features that the cameras are picking up are the equivalent of pillars, right? So the camera tracks these features from frame to frame, and the IMU on board is measuring the motion of the camera. So the things that have to be estimated online are the relative position, the relative orientation, and then the positions of all these features, the 3D positions of all the features. What you see here are the 2D positions that you see in the retina. Well, each of these problems can be decomposed into smaller problems, and in each of the smaller problems, essentially we're assuming that 2 of the 3 things are known and the 3rd thing has to be solved for. So if you decompose it in that way, the problems are either linear or convex, and again lead to provably correct solutions in terms of these sub-problems. Of course, the whole problem is nonlinear, and one can try to solve the whole problem and then get into difficulties in terms of actually getting real-time performance. And so this shortcut essentially allows us to get a 100 Hertz estimate of, again, the positions, velocities, and so on for real-time control. So I'll show you a video that illustrates some of the estimation results. So this is essentially the features that you actually see in the camera, and you can see this robot actually flying quite aggressively with roll and pitch angles of 30 to 40 degrees. And again, you can't really use linearized controllers or linearized estimators for this. The key point I want to make here is that it's actually able to track these features, and in this picture you see its ability to actually track, to estimate the reference frame. There's also ground truth shown here, and this shows the performance of the estimator in 6 dimensions. I think even more impressive you'll find are these video clips. So I want to show you on the top left, you'll see our robot flying 4 meters per second indoors. So that's actually a pretty brisk pace. If you look at your walking pace, it's about 2 meters per second. So it's about twice walking speed. This is outdoors. This one is sped up, but the key thing here I want you to notice is in spite of all the downwash from the rotors, you see the foliage that's moving rapidly. The robot can still find enough features to track as it flies. This is in a 3-dimensional environment. This is actually a much longer flight where it's actually taking all the features that it's found and building a grid-type representation and creating a map. So this map may not look as nice as the map I showed you earlier with the laser, but it's enough for the human operator to actually drive the robot remotely. So if you know what this map represents, that's enough for you to command the robot. And then finally, our most capable system is this one, which has not only the 2 cameras, but also a laser on top and a GPS unit. So the reason we want this is we want to use whatever sensor works. And in this video clip, you'll see this is about a half a kilometer flight. You'll see in wide open areas, the only sensor you can get is really GPS. So here there's only GPS. Here's the covariance ellipsoid that's estimated by the robot. But as it gets closer to the buildings, you can see that it actually, the laser detects these walls, and it's able to triangulate using the GPS and the laser. And now you'll see it flying through this clump of trees where, in fact, GPS does not work, but the camera does work. And it's able to use the camera and the laser to localize itself. And when it goes indoors, as you'll see in a minute, again, GPS fails. So depending on what sensors are available, the robot's able to integrate information, fuse it into a reliable state estimate. And again, this is Xiaoji Shen's work. So this is, I think, pretty remarkable in the sense that you have a fairly robust capability. Regardless of the environment, the robot's able to localize and function autonomously. So having said that, there are a couple of environmental features that will really throw the robot off. For example, glass. I mean, even birds have, I mean, human beings have a hard time when you walk in, you know, I'm sure you've seen people walking into glass walls. But birds fly routinely into glass walls, and the problem is cameras don't see well on glass walls. The lasers also don't work too well. That's one problem. The other problem is with smoke and dust. So you need other kinds of sensors. But in most settings, these kinds of sensors do work. And again, the idea is that you want to piece together as many sensory inputs as possible and build a robust filter out of it. So let me stop here and see if you have any questions before I move on to the third piece of the talk. Yes?
You use for keeping?
So the laser actually has a 270-degree field of view. But if the robot's going forward, you really have no use for the part that's behind you. So what we do is we arrange mirrors that deflect some of the beams behind, pointing up and pointing down. And that allows us to, but if you don't have a laser, the thing you want to do is use a barometer. So you don't get very good estimates of height, but it's enough for the robot to work. And remember, you also have an IMU on board that gives you some measure of the Z acceleration. Yeah, you can actually map the terrain underneath you if you needed to. Yes?
When you have the laser sensor, why did you need it?
So a laser, so ideally you want a three-dimensional laser. So if somebody could offer to me a three-dimensional laser that was lightweight, low power, and inexpensive, I wouldn't buy it because I know it wouldn't be true. But that's what you really want. So the problem with this laser is it's two-dimensional. So if it's two-dimensional, you just think about it, there's no way you can take off because you don't know what's above you. So you need something above you. So Kinect gives you this 40-degree field of view that allows you to actually look at things on top. So which means when you fly, you can fly in angles that are 40 degrees to the horizontal, at most 40 degrees to the horizontal.
To do the feature-based so we extract features, estimate the altitude.
Well, right. And you also want to make sure there's nothing in front of you. So if you take off this way, you don't know what's on top of you, right?
Yeah.
But if you're looking in this field of view, then you can take any trajectory this way because you have complete visibility in front of you.
Right. So the laser sensor, you pretty much have to do the view basis. The fact that you're doing the features.
So I'm not talking about SLAM or anything like that. I'm just talking about basic awareness of what's around you.
Right.
Right? So if you have a planar
The
sensor,
reason I'm asking is
yeah.
that like if you use the camera to detect the obstacles, so either you have to do feature extraction or you have to do the views and assume that you have to extract the feature and estimate the with maps.
correct. So if it's camera based, we're tracking features at 25, 30 hertz, and we're able to build this at 25, 30 hertz. Yes.
Right. Then how can you tell that whether it's an obstacle or not with the camera?
That's a great question. So technically, you're right. So unless you have a laser, you really cannot. With a Kinect, you can because it's a depth sensor.
Right.
So with a camera, if you don't find features, that doesn't mean there are no obstacles in front.
Right.
Right. So there is a finite probability that you're going to fly into something. That's why we have this cage around us. And so oftentimes you bump into things and you know there's something there because you bumped into it.
Right.
This is like a blind man sort of looking for walls. So that's also important. Yeah. Yes. So certainly power is a challenge. One question you can ask is, if you're only given 10 minutes, what can you do in the 10 minutes? Right? And rather than say, well, I want to wait till I get the next generation of batteries, or my favorite is small rocket engines, because rocket fuel has the energy density and the power density. The question you can ask is, how can you perform whatever you need to perform in 10 minutes? And most likely it's going to mean move faster, move more quickly, get the information more quickly, and get out. right? And that's what we'd like to work on. Any other questions? Yes? There are, yeah, there are a lot of open source things. So, for example, if a lot of the point cloud libraries that you see for visualizing the data sets, those are all open source. All the vision stuff is based on OpenCV, which is, again, available open source. Navigation, we do our own. Yeah. Okay. All right, so let me talk a little bit about creating lots of these robots and getting them to cooperate in performing tasks. So I want to just give you some examples of what the challenges are. So I want to show you first what it means to have a small team of robots collaborate. And I want to show you the work of Quentin Lindsay, where he basically figured out how to get 3 robots to collaborate in performing assembly tasks. So here the assembly task is trivialized in the sense that all the building blocks are truss-like modules with magnetic fasteners. So the assembly process itself is pretty trivial. You bring it into position and it's going to snap fit. But the key challenge here is to essentially have the robots figure out who's going to pick up what part and assemble it where. And they're all doing it from a very simple blueprint of what the structure needs to look like, not unlike a 5-year-old opening up a Lego booklet and saying, hey, this is what needs to be built, and I'm going to pick these blocks and put them together. So that kind of intelligence is essentially built into the system, and the robots figure out how to coordinate in order to build this task, build these truss-like structures. And here you see 3 different truss-like structures, and each one of these has been sped up a little bit. So there's a lot of coordination involved. Robots have to figure out how to plan paths, how to make sure that these paths don't intersect each other, and also make sure that they get the assembly done the right way. So the problems here, if you think about scaling up to large teams, you have 2 types of problems. First, when you have lots of robots in the same space, you have to worry about collisions. So the problem of resolving conflicts scales quadratically with the number of robots. The second problem is this question of who goes where and does what, right? So this is a combinatorial problem. So this grows as n factorial. So both these problems are kind of swept under the rugs when n is small. There's only 3 here. So we want to solve these problems for large numbers. So let me just throw out a few ideas on how we might approach this. And again, it's useful to look at nature. So this is a picture of about 500,000 starlings of the coast of Denmark assembling to form these amazing patterns. And you can ask if actually they explicitly coordinate with each other. Is there a central individual that's also telling them where to go in order to form these patterns? You can also look at more complex tasks. So here are ants assembling to form this complex bridge. Here are ants actually collaborating to carry a large object. In case you're worrying why this laser-cut plastic piece is being carried by the ants, well, we coated them with the juice from figs. So they think it's food and they're carrying it back. And the interesting thing about it is you can actually tell which ants are pulling, which ants are pushing, and which ants are just goofing off and doing nothing, right? Because the arms deflect and you can kind of figure. So how do ants do this? And or migratory birds? There's a recent study in Nature that shows that that the birds save about 20-25% energy by just synchronizing the wing beats. Not necessarily maintaining the shape, but making sure the wing beats are actually synchronized in order to minimize the amount of fuel consumed. So these are good problems to study to figure out how we can get robots to behave the way we want them to behave. In all of these systems, you can come up with sort of 3 organizing principles. First is this notion of acting independently. There's no way you're going to have in any of these examples one of the ants or birds essentially say, this is how everybody's going to do things, right? So this just does not work. The second idea is this notion that each of these individuals acts based only on local information. So there's no way that ants over here know what's happening to the swarm at the other end. Or even in this case, actually, these ants are surprisingly unaware of ants on the other side of the object. And then lastly, there's this notion of anonymity. Ants are pretty much agnostic to who their neighbors are. Birds are agnostic to who their neighbors are. If maybe a group of us, 3 or 4 of us, had to pick up this table and take it out of the room, we wouldn't care too much about who is joining the team, right? We would be fairly agnostic to who the neighbors are in that task too. So all of these things have to be incorporated into robot control algorithms. So let me just show you how we try to emulate or incorporate these 3 ideas into our control policies. So the first idea is this notion of having robots that are aware of their neighbors. So we do this by having robots keep track of the relative separation where, again, xj is the position of robot j, xi is the position of robot I. But remember, we're dealing with this flat coordinates, so we ask them not only to maintain awareness of x, but also the yaw angle psi. So these are called shape variables. And there are as many shape variables as there are neighbors on the graph, or pairs of neighbors on the graph. So we have all these shape variables that all need to be regulated. And we have 1 or more leaders that are actually figuring out how to move. So this is, again, in that flat space. Again, this is the yaw variable, and this is the xyz variable. We can form these leader-follower networks where there's one leader. This is, by the way, a guy by the name David Pogue who writes for the New York Times. He actually writes a tech blog. It's quite an interesting blog if you care to read it. And so he wanted to see if he could actually command the swarm. Now, it's not really a swarm. It's only 4 robots. But our lab is small, so we can't do very big groups. But you can see that just by controlling 1 robot, he's able to control this entire team. The whole idea is that the complexity in the task is reduced significantly when all you have to do is worry about this 1 guy being controlled. By the way, this is the work of Katie Powers, a graduate student. So, again, David is essentially playing the role of a coordinator without explicitly commanding all these other robots. They're essentially following their neighbors and making sure these shape variables are maintained. Then this notion of anonymity, and this is work of Matt Turpin. If you make robots anonymous, surprisingly, the n factorial problem actually gets simplified, and it becomes order n cubed. So this is an algorithmic trick. But the idea here is that you can see David deploying these robots, and the robots essentially react to their neighbors. They've been asked to form a shape, so when new robots get introduced into the formation, they automatically spread out in order to form the shape. When robots go away, they again squeeze to form the same shape. So these kinds of behaviors happen naturally, and once you have these basic building blocks, what you can do is create shapes and have the shapes move as a function of time. And you'll see the formation shape change. So they start off in a rectangle, they flattened out into a circle, and now you'll see them straighten out into a straight line, and then go back into an ellipse. So the commands that are being issued are essentially the mathematical description of the shape and the 3-dimensional position of the shape. These high-level commands are independent of how many robots are there in the formation and who the identities are. And the computations are essentially constant. They don't scale with the number of robots. So that's pretty important to make all of this work. So this is the largest team we've actually done in our lab. There are 20 robots. And again, this is done with the motion capture system, so the robots actually know exactly where they are. They also know where the neighbors are fairly precisely. And you'll see, again, the formations changing shape, changing position orientation, going from 3D to 2D, reacting to obstacles in the environment, and then changing shape to squeeze through the obstacles. And then finally, you see this sort of figure 8 pattern. This is sort of the top view, and you can see fairly precise coordination. Again, robots reacting just to their neighbors. So why are we doing all of this? Besides making cool videos, why worry about swarms? Well, let me just show you an experiment that we did in Sendai that motivates some of this. So this was done with 2 robots. This is, you can see our big robot with the Kinect and the laser. And then below it is one of the robots built by Tohoku University, which is like an iRobot PackBot, if you've seen that. And this was used in the Fukushima reactor buildings. So you'll see our robot sitting on top of this. It's being held by a landing pad, which actually retracts and closes. When the team is confronted with an obstacle, it retracts and lets our robot take off. And you can see our robot building a map, going into this room, going on the other side of this bookshelf. Again, things that a human being couldn't do in a collapsed building. And you'll see it go into a neighboring room now, which has all these pipes that were erected to protect against earthquake collapses after the first one. It's able to navigate that. Again, the ground robot would have gotten stuck, but the aerial robot's able to navigate. And the key thing is that the information gathered by the ground robot and the aerial robot could be integrated, and we could create maps like this. So this is a map of the 7th, 8th, and 9th floor of the electrical engineering building at Tohoku University. So this experiment took us about 2.5 hours to complete. So you can imagine if you had an earthquake and you want to go in and look for victims, you don't have 2.5 hours. You don't have the luxury of that much time, right? So you want to do it really quickly. You want to do it in 2.5 minutes, if not 2.5 seconds. And that's the kind of capability you can build in if you had, let's say, a fleet of 100 flying robots walk in with the same kind of hardware. But now imagine that they're smaller by a factor of 5. So 10 minutes is plenty of time. We should be able to do this, and we should be able to create these kinds of maps. So that's where our research is taking us. We'd like to be able to coordinate these robots to collect this kind of information, but again, do it several orders of magnitude faster. So let me conclude on a light note. I want to show you a video it's a fun video. So this was created by my former students at KML Robotics. It has some audio to it. Okay, so that's computer graphics. And it has nothing to do with cars, but anyway, so this is sort of the vision for swarms, and I'd like to conclude with a poster. This is a Warner Brothers movie. If you've not seen it, I recommend you don't see it. It's not a great movie. It's about killer bees and attacking human beings, but the poster, in some sense, everything about this poster is correct. The size is immeasurable. The power is limitless. In some sense, its enemy is man. It's human beings, because this technology is here. The question is, do we know how to use it? And can the economics work in our favor to actually deploy this technology? So all the building blocks to do this are here today. And of course, we want to channel it for things that are meaningful, such as in search and rescue operations. So let me just conclude. There's a final yoga pose from David Pogue. So thank you very much.
You want me to land?
I cannot do this. This is questions. Yeah.
Thank you very much for my question is more on a few biological examples, like technology, there are a lot of cell organization behavior people have been.
Yeah.
So in your view, what could be limits of inspire algorithms, body system. So you what could be the, for example, how fast can we for the robots? Once, because a lot of battery issues actually flying robots, but if it's one robot, those concerns are actually much less robot to build many different things. So, points that how important to follow those biology understanding, even those knowledge is available, what could be biggest limitation of it?
I mean, that's a great question. So I think it's always good to study nature to see what you can learn. But oftentimes the solutions that nature offers were constructed for different sets of boundary conditions. So if I want to go in quickly and get specific information that's of interest to me, it's unclear that you can go out in nature and find similar types of problems, right? So in the kinds of things that I was talking about, I think it'd be very hard for us to expect a self-organizing group of robots to go get the information in the timescales that we need. Having said that, I think your contrast between ground and aerial robots is a good one, and perhaps also alludes to the fact that there are some missions where time is not enough in a sense, where in fact you can allow things to evolve slowly and for the patterns to get established and the self-assembly to get the task done. And assembly is a great example of that. But in our kinds of applications, we want to abstract away at a sufficiently high level and pull out what we can get and then tailor it to the specific task that we're interested in. Yeah.
I think there are still lots of questions, but time constraint, we will take one more question and then you can discuss afterwards.
It's just a quick question. I'm a little bit confused about your setup. So your state estimation robot was motion capture.
In this case, yeah.
In this case, where are the controller on the?
Yeah, so in the middle I showed you robots that were completely self-contained and could work on their own. And then I digressed into a system where we actually did use the motion capture camera. So I went back to that. But again, if you want to build 20 of these with onboard cameras and laser range finders, we're not quite there yet, but we're getting there. So this system actually does have information from the motion capture cameras, but essentially the information about their neighbors is obtained by communication and not with onboard sensing.
So the motion capture forecasting.
Right, so it's like a cloud computing type setup because the cloud knows about every robot's position and the robot can actually interrogate the cloud to get its information and find out where its neighbors are. So that's the setup being used here. Yeah.
Okay, so I know there are lots of questions. Oh, okay, last one.
No, it's not a question. We're scheduled till 5.
Oh, to 5?
Yeah, it's an hour and a half seminar for ISU.
Oh, okay, sorry.
He wanted to leave and you just cut him off. Yes.
Your swarm does not require communication as another.
No, they do require communication with each other. So you can either communicate or see each other. So our robots these small robots don't yet have its sensors, so they rely on communications to coordinate with their neighbors. Does that make sense? So I think without communication or sensing, it's hard to establish any kind of organization or have any organizational principles.
Okay, so Vijay, I know that we have 5 to 5,
Yeah.
or time to 5, and some of us probably need to go for another class. So you can still ask a question. So
I'm here.
Let's temporarily end the talk, and many, many thanks
Okay.
for the wonderful talk. Okay,
Thank you.
Thank you again.